stimulating discussion on the different aspects of liquid crystals, and also to a very interesting and nice city, which yesterday I visited a little, and really I was very surprised how interesting and how nice is the environment. And today I would like to say a few words about our recent research in the studies of confined nematic phases, where they are confined in fact by the presence of colloidal particles. So that means the discussion will be about the assemblies of particles in nematic phases. First perhaps to mention the co-workers. So the main co-worker is in fact my former student, who mostly have done the work which I will present. Then we have in part a collaboration with theorists in Oxford from Julia Guillemets and Gareth Alexander. And then we have a lot of collaboration with our experimental group in Ljubljana, led by Professor Mušević. Now, what I would like to say is first a little about motivation, and then further about our approaches, and then about defects in liquid crystals, and then particularly about the assemblies which are we will study. Assemblies are in a way dimers, so two particles and then more particles together in lattices. In the end, we will be interested particularly in the possibility of going from one dimension, 2 dimensions to 3 dimensions. So assembling particles in 3 dimensions. And an example will be colloidal blue phase. Now about the motivation. Motivation for this study was coming mostly from the experiments which were performed particularly all around the world, but more recent ones were coming from the laboratory from Professor Mušević, where they have observed very challenging textures, and we tried them together to understand this. So besides the other part of motivation for this study is also the basic interest in topological aspects of complex arrangements of colloidal particles. And the third aspect is also that there is a possibility that these arrangements of colloidal particles in this template, nematic or cholesteric or other templates, would lead toward some photonic applications. And if I go first to our initial system, which is in fact a very confined layer of liquid crystal, where colloidal particles are somewhere constrained to a very narrow layer. So that means the diameter of the particle is comparable to the thickness of the layer. And then we have strong anchoring on both sides of the layer, and then partially strong anchoring on particles, where now one could have homotropic planar, it depends now. For the layer, we will mostly discuss the case when the two surface conditions are parallel to each other. So that means a homogeneous cell, and in part we will discuss also a twist cell. So that means that the two directions of two surfaces are orthogonal to each other. And now if I go to our approach is the most simple as possible, or at least going from the phenomenological point of view. We are using the Landau-Desgen type free energy, which has the gradient terms, including the chiral term, which will be relevant particularly for blue phases. And then we have the phase term, which we have the order parameter, and then we have surface coupling term, which determines the coupling of the surface. So we really try to stay as simple as possible, so that means use just one elastic constant. It's clear that this is not enough for describe our situations, but it gives you the crucial in-view in this possibility, impossible structures. Now, about the numerical procedures, because in most cases you cannot go with the analytical procedures very far. There could be limiting fields, director fields could be certainly well described, but we need more than this, particularly because of defects. So we used numerical minimization of the free energy, and to cover very well the situations also on micron scale, there was a really need to have a lot of mesh points like 10 millions, because our resolution is somehow determined by describing the defects through the nematic correlation length, which is few nanometers that we know. And that means to get in equilibrium in such a state, usually we need between 10,000 to 100,000 steps. Now, boundary conditions, as I said before, that we have strong anchoring on the layer, which is confining the nematic, and then we have a colloidal particles of this surface free energy, and then we have on the sides, which means that if we create this two-dimensional system, we have periodic boundary conditions, which in some way limit also what we find out, because if we would have a bigger cell, cell where we would solve the problem, we could also find situations which are going beyond simple few nanometer scales. But we were limited by our computers to some extent. Now, what is very well known about the defects, there are very known features, and there are discontinuities in the director fields, and they are related with associated with strong variations in the order parameter in the tensorial meander. So that means either by axiality, degree of order, direction of the main principal axis, and so on. Now, what we need here, we will have mostly line defects. Point defects will be just practically not present, because and these line defects in our cases will be in most cases -1/2 with the winding number -1/2. This is a kind of such a line, but these bricks here are representing a kind of local order, and if you go around, so we have this 180 degrees turn. And what is here also important, that in the core of the defect, as I said before, we have strong variations. Now, if we have, for instance, the defect +1, which is not the most stable association, and it escapes in third dimension, so that means the director, if we represent it by this short cross, is not as singular in this case anymore. And we will see later on that in some particular case we will need some of this. And now about the visualization of our results. We can use either director by plotting bars or lines, or this like this spherical or this cylindrical objects, or we plot surfaces of constant order parameter, or perhaps by axiality, or in case when we have this non-singular defect, so +1 with this escape pole, we plot the area of constant inclination of the local direction. So these will be our presentation of the results. So these well-known results here illustrated on these situations when we have homotropic anchoring condition in a thin layer with planar or homogeneously oriented liquid crystal. In this case, we have this well-known central ring deformation, which is have a quadrupolar. We have this dipolar symmetry, where we have this external point defect, which is in fact not a point, but is a small torus. And we have then the colloid here, which represents the other part of the dipole. Or in the planar arrangement, we have these two bosoms of the two sides. These are our presentations, so that we show colloid and then the defect line. Here in this case, for instance, what defect line means the surface of constant order parameter was here taken 0.5, while the bulk is 0.533. So that means we have some depression of order in this area, and we plot just the area of constant depression of order, what gives you our presentation of this declination line -1/2, which is in fact in the Saturn ring. Now what will be more important further is in fact the interaction between the different colloidal particles, which is mediated by liquid crystalline ordering in between. And so this interaction in this case is mostly related to how the free energy minimizes. That means if we have a depression of order close to the colloidal particle, or increase of order close to colloidal particle, then you share usually this depressed order area, and in this way reduce free energy. So that means the interaction comes mostly from the sharing of the deformed order parameter field. And this kind of interaction, effective interaction, is long distance. Now, how long distance, this depends now. In the layer which is strongly confined, as is in our case, we have power laws for the distance dependence, and we have so-called screening on larger distances, because then what prevails is in fact the anchoring on both sides of the confining layer surfaces. So that means for us we are interested to interactions on rather short distances where screening is not effective. What will be later on shown also is that that this interaction could be also in such a way that you share declination lines, not only deformed director field. And this leads to some called entangled structures, where interaction becomes string-like, so that means it doesn't depend on distance. And we will see that this can happen either for singular defect lines or for non-singular lines. Now if I return back to this case of dipolar pair, which is a known situation, so we have this in our presentation, two such dipoles, so they can arrange in this way, or they can arrange in a line. Both structures can be visible, and they are a building block for a bigger arrangement, either in one dimension or in two dimensions. And so it's the similar situation with quadrupoles, so two of these Saturn ring orientation structures do not interact in this direction, but they interact with some other angle. And if we look at the detail, we see that when they come close together, they also deform the Saturn ring. So that's a kind of solution when they are rather close, and that's an equilibrium state which gets the which corresponds to minimum of the free energy. And again, this is then a building block for further association. One can associate like also dipole to quadrupole together, so they in such a way, and we see again we have deformation of this declination line, or in this way we see that this dipolar ring expands in this case, so it's no more point, but it's a more substantial object. And again you can build quadrupolar lattices. So here I show one example of this lattice, so you can have arrangements where you have dipolar chains, and for instance there's experiment here, and this is a simulation, so we have dipolar chain, and then we have this quadrupolar arrangement, and then again dipolar, quadrupolar, and this is an experiment which was performed also so that instead of having two dipoles or two quadrupoles, they can change into a structure where you have a single slope destination line which couples two of them. And there are three examples of such lines. This one is not a single one, but it's a combination of two. But again, we have a kind of arrangement going around two of them. And here we share, the colloidal particles are sharing the destination line. And this destination line topologically corresponds to the two Saturn rings. So the charge associated with this destination line here, or this here, is 2 instead of -2 instead of each simple loop which has the charge -1. And this additional charge comes from this twist here in between, because this figure of 8 is twisted. And it could be left or right. If our environment is homogeneous, then both are equivalent. But one can build more complicated associations, like 3 particles together here shown. It was represented in soft matter recently, and so it's a trimer. And in that case of trimer, you can have a lot of arrangements which are all more or less equivalent in energy. Now, one can arrange this further in 2 dimensions by simply having a braid where the single line can go practically anywhere. The question is if in experiment you can perform this. It's shown that this is practically impossible in the usual homogeneous cell. While these 2 of them is easy to assemble, which I showed before. So this is assembled in a way that they start from this situation here, melt this area in between by laser, and then they fuse together in a single stroke line. That's the usual way how they make them. But if you want to make larger arrangements, that situation means that it's perturbing back and it does not work. But if we have the environment, which is we call twisted, so that means that we have outer director field such that it's on the upper level, it's in this direction, then it's for 90 degrees twisted. So usual twisted cell. Then 2 of these quadrupolar structures, so these Saturn rings, are like this. So they are a little tilted against the previous direction. They are deformed in a different way, but they still exist this equilibrium state. But if you push them together, they simply fuse, and you can get this situation, figure of 8, which occurs so can be formed experimentally in an easy way. That means that the free energy barrier between these 2 states is much smaller than in a homogeneous cell. And that means that the twist cell is somehow opening additional possibility to form these structures. One should mention that there are then left and right twists that are no more the same, because of the internal director structure is twisted. So one is observed, the other one is not observed because it's unstable. So one can easily see that things could become even more complicated, so that one can make also links, like this off link could be created by 2 colloidal particles together with 2 destination links which are somehow coupled together. Experimentally, they haven't seen this in the case of double, but in the case of more colloids, these links and also more complicated knots can be observed and even made somehow in a predicted way. And also in the modeling, we can easily predict how energetic are these. This energy of such a state is like 10% higher compared to the previous, which I showed for a figure of 8. But nevertheless, it's possible to create this, was shown, but I don't show here all the results because we are not yet at the end with the explanation of all steps. Now this is another situation which which is an assembly of the two particles when the dipole is oriented one against the other. If you push them together, so this dipole, this point defect here spreads in a ring, and then you have two rings which together have each one minus 1/2 winding number, so that means charge -1. But they can fuse together in a single ring of charge -2, running like this, which is of this hyperbolic cross-section. So it's in fact the escape structure. So it's a -1 ring coming here around between the two particles, and it links them together. So that means it's a stable structure. Now here is presented in our presentation. So this destination line is non-singular because we have here inside such an escape of the director in the two directions. So in fact there's inside also a twist, so as a twisted direction in this direction. So that is a detail in the inside here. And there is no singular director point anywhere, but what we plot is the inclination of the director. So that means this is the central part of our non-singular -1 destination line, which bonds together these two colloidal particles. And this one was observed first by Fulan like 10 years ago, and then explained by Fukuda and Yokoyama 3 years back. And we see that this is much better, much more stable in a twisted cell. And here we try to understand how it works in a twisted cell. In a twisted cell, we have the external twist, and this line itself is also a twisted structure. And both together will form this, that you have two possibilities. Either the twist goes in the same direction or opposite. So what it selects, that you have two types of -1 destination lines, which one is more stable than the other. Both can be realized experimentally. These are the cases, and this is our simulation here. And globally looks very similar, but if you look in the details of the lattice cell, they are different. So that means we are able to put together an explanation of this two-dimensional lattice based on this -1 destination loops, which is observed and can be stable and can be also discriminated depending on what kind of twist is present. So now I go to the last stage of my presentation. I think I still have a few minutes. 10. Okay. Yeah, to present an attempt to go to 3 dimensions, because with what I showed till now was structures in 2 dimensions. Now, idea is like this, assembling 2 dimensions of these quadrupolar structures, Saturn-ring structures. That's a stable one observed experimentally. The question is, can we go to 3 dimensions, so have this kind of step? If you look a bit more precisely, you see that it's not a simple static of 2-dimensional layers, because these colloidal particles are shifted up and down, so that means you cannot simply put such a layer on top of the other, at least not in the experiment. Now we can certainly run a modeling simulation, which then gives us what is the predicted structure. But till now there was no experimental realization of such a 3-dimensional colloidal lattice based on the Saturn rings. Now here is another situation based on the 2-dimensional dipolar lattice, which I showed before. The dipolar, these these associations go into chains, and then chains then assemble in 3D, so you get this kind of in 2-dimensional structures. What was proved by experiments very well, and what is works very well. The question is, what about 3-dimensional stacking of this? So if we want to down and again up, down. So there is a simple lattice which is organized through such dipolar chains. And here is a more precise simulation picture which shows that it exists, it has a minimal energy, so that means it's stable. The question is how to make it. That means it's a challenge for experimenters how to put these chains of dipoles together in the three-dimensional stacking. Till now was no real success yet. Therefore we try to see if there are other ways to go to 3 dimensions. And the idea is to start with the assembling of small colloidal particles, or not assembling, in fact attracting small colloidal particles in the destination line. So if you have this -1/2 destination line, it is in fact an attractive point or attractive area for colloidal particles. They go inside. Why they go inside? In this way, in fact, the free energy is reduced. Because inside the formation is the highest, and if it's substituted simply by the colloid, it means that you have a state of lower energy. And this is such an arrangement, here predicted for a Saturn ring, full of colloidal particles, and it was clearly shown in experiment that this is easy to realize. So that means this works, and what was done was experimental studies were usually in case where you have several micron size of one, and one was close to the little submicron. But one can have bigger differences, more tiny particles, larger big particles, so all kind of possibilities. The idea is this a start towards 3 dimensions? Perhaps. So the possibility is coming from the destination lines in blue phases. So these are a representation of the 2 blue phases. Blue phases are in fact coming from cholesterics, where you have a more complex arrangement of twists or double twist cylinders. So these here are schematically presented double twist cylinders in 2 stacks. And here, what we present here are destination lines. So these red lines here are in fact destination lines of -1/2 again. And we have a 3D arrangement of these lines. And these are now a possibility to be an attractive structure for collecting colloidal particles. So that was the idea of 3-dimensional thing. Now, there is a lot known about the blue phases, but they became more attractive recently because people now know how to make a wide range blue phase. Before, blue phase had a very narrow temperature range. Now it's possible to make it in a larger. So there are also now here some recent studies mentioned. And now so here I present a little additional graphics beside the defect lines that we present areas where where free energy has the lowest value. So that means these areas here between free energy density is the lowest. So the colloids will avoid these areas. They will go to the areas where we have the highest free energy. So these are in fact the areas along the destination lines as we know before as well. And this is the situation here presented for the blue phase 2. So the highest energy here is lower, so that means colloidal particles will go here, not here. And while in the blue phase 1, they can distribute in fact anywhere along the line, more or less anywhere. Now, these are the predicted structures of colloidal particles. Your right number of colloidal particles to cover, for instance, here all crossings in blue phase 2, or to have 1 per unit cell in this blue phase 1. But one can have less particles, then they will distribute in a different arrangement. But nevertheless, all these structures here are somehow minimized through free energy, so they are in principle possible. The question this will self-assemble. If you mix blue phase together with the particles, will this arrange or not? Now that must be still explored. What people have done till now is study very tiny particles, like nanoparticles. They certainly assemble in colloidal lines, but don't form a very nice lattice. So therefore, we are more interested for photonic lattices, which would have bigger particles, which are, let's say, a part of the lattice cell. So if you have, for instance, particles of 200 nanometers or 100 nanometers to assemble and then we made the analysis of stability. It looks that all these structures are rather stable to the perturbations. The question is now how to realize them in the manner of assembly. Here is also a study of the effect of anchoring. So better we see that it's easier to stabilize bigger particles if they don't have strong anchoring. So if you have strong anchoring, only the tiny particles can be used. No, but that is something one can expect. But we have also shown this, that the situation. The other thing what happens is that the blue phase range is also expanding. So the phase diagram of blue phase, the range of blue phase 1 and blue phase 2 is expanding by adding the particles. So that means it can even expand for a factor of 2. Now depending what kind of particles, what kind of size, anchoring and so on. So that means there is a perspective here for making self-assembly of 3D structures. Now, if I summarize this, what we have shown here, that sharing of a deformed field and sharing of discrimination lines is a main mechanism for organizing these mesoscopic structures of colloidal particles in nematic or cholesterics and probably also in other fields of liquid crystalline states. So in particular, another addition was that twisted nematic cell is a good environment for more complex arrangements, which includes also knots and non-singular discrimination. And then we have seen that three-dimensional structures are not directly observed, cannot be directly made by simply stacking 1D and 2D structures. And then we explored a little the possibility of blue phase to go into third dimension.
Thanks. Thank you very much. Yes, is a comment.
Do you have an idea how to use particles, colloidal particles, to put them into nematic? And
to put them into what?
Yeah, into nematic, for instance.
Yes.
And produce cholesteric phase or blue phase. What you're saying?
Do you mean to produce nematic or by adding simply particles, or cholesteric by adding?
You're doping blue phase with some particles.
Yes.
And they arrange somehow, right?
Yes.
What I'm asking,
if
you have an idea how to make blue phase from non-chiral phase by adding some kind of particle? Any idea?
Yeah, I don't know much, but I would expect that then if you have particles which have some particular imprint on a pattern on it, which could have a chiral pattern on the particle. So to do something on the particle, or perhaps a shape. No, I think that Ivan makes particles with shapes. Why not to make them twisted? Then arranging in the nematic, they will induce a chiral structure also in the nematic. Depending now on density, they will be expelled or whatever. But there is certainly probably a range where this can work. That's the guess.
I have a question. How small particles could be used to produce those two-dimensional arrangements that you showed in the beginning?
Yeah, so like the 2D lattice. One can have rather small ones, but now if you go down and down with the size, then this energy which is associated with the coupling in the field, nematic field for instance, is going down as well. And so if they reach the nanoscale, then the energy comes close to kT. And that means they are less, so the structures are exposed to fluctuations, thermal fluctuations. While here energies are extremely high, like 10,000 of kT and so. So fluctuations don't do anything. So that can be the...
So
yeah.
Do you have some quantitative numbers?
Yeah, we have tried to see how this coupling goes down with the, let's say, size. And the anchoring, both are playing the role. So, and particularly we said, okay, if it's too small, it's not trapped in a declination line, simply because if you have a declination line, then particle can be inside or outside if the energy is comparable to kT. So that means, and it comes down that in a few nanometer sizes, that's certainly the case. Now really depending on anchoring to some extent.
Thank you very much again. Next speaker, Ian Lucas, that is talk with title Nano-based integration illustration. 35 minutes and 1 minute question.
Okay, so hello everybody. So I'd like first to thank the organizers to invite me to talk today. So this is a work I'm presenting which has been done mostly in Boulder with Noel Clark and Matt Blazer. And so some of the simulation presented has been done by Matt and some by myself. So I will talk about this problem of phase behavior in these band core molecules. So our motivation is to study this band core molecule. So they present a very complicated phase behavior. So there is different points which are important. So there is, so I will go back to this point. But so there is this problem of this spontaneous chirality, which appear in the system. There is competition between the clinicity, so the way the molecules are tilting in the symmetric layer, and polarity, because these molecules are bent. And there is a very, very rich zoology of colonnar and the splay modulated phases, so something which is not very well understood yet. And there is also interesting phases. I will not talk at all about it. I just show you some information. It has been done mostly in Boulder on these phases before and this dark conglomerate phase. And so what we are doing ourselves, we are trying to explore this microscopic origin of this behavior, and mostly using coarse-grained molecular simulation, and we have plans to use also atomistic simulation, but we didn't do much on this yet. Well, just to go back to this thermotropic liquid crystal, so when you are at high temperature, you have an isotropic phase where you don't have any long-range order. So then when you decrease temperature, you can have, well, it's made by molecules which are rod-like in shape. So when you decrease temperature, you can have a nematic phase which has long-range orientational order, but no long-range positional order, and decreasing again the temperature, and if the compound allow you can have the formation of layers. So you have a stack, a one-dimensional stack of two-dimensional liquid layers. So inside the layer, you don't have any long-range positional order. And then when you decrease again the temperature, you can have tilt of the molecule, and you have symmetric C phase, where the molecule is tilting with respect to the normal, to the layer. And then going one step further, if the molecule is itself chiral, so if there is a chiral center in the molecule, so for example here, this chiral carbon in the molecule, then the symmetry of the symmetric C phase made by a chiral molecule, plus the fact that you have chirality built in the molecule, give rise to some ferroelectric phases. So some phases which are chiral, so means that they are not superimposable to their image in a mirror, and so you can have molecule from one layer. So you need to read this stuff in this direction. So you have this magnetic C, which is ferroelectric. So here, usually this chiral center is carrying electric dipole. So you have some polarization which come here outside of the screen, and so you can have the same tilt in the same direction from layer to layer. So you have something which is ferroelectric, or you can have molecules which are alternating. Their tilt is from one layer to the other is in opposite direction, and so in this case you have something which is antiferroelectric. So this one is made only by molecules which are chiral. And so recently, there is this new class of molecules which has been synthesized, and so these molecules, they are characterized by the fact that their rigid core, instead of being linear, is bent. So you have a bend of the molecule, and the molecule by itself is not chiral. So there is no chiral center in the molecule, but you can have two symmetry breaking. So these two symmetry breaking are presented here. So you can have the molecule when they form symmetric phases. So you can have a tilt. So the molecule tilt with respect to the normal, to the layer. And the fact that they are this band shape means that the molecules are packing to each other and they form in the polar plane. If you turn from 90 degrees this view here, if you turn from 90 degrees, you have this packing of this molecule. And these two breaking of symmetry make that you can have some phases which are here, presented here, which are not superimposable to their image in a mirror. So what's interesting is that you have chiral phase, so this one here, so the S here means that the molecules are tilting in the same direction, so it's magnetic C, it tilts in the same direction, so it's synclinic, and it's ferroelectric. But you can have also something which is antiferroelectric, and so these phases are chiral, and you can have also here, because you don't have chirality which is built at the chemical level, you can have also racemic mixture of two different chirality in the system. So you have more, you have the phase diagram is richer in this case. So the interesting point is that the molecules are not chiral, but the resulting macroscopic phase are chiral. And so there is also more complicated phase which can happen in this system. So you can have also a modulation of the polarization in the system, and so you have this kind of phase where you have modulation of the symmetric layer. Is this phase which is called B7. And you can have also the breaking of the layer in blocks, which are presented here. And in fact, these two phases, they are kind of connected, and we think that the system, there is a lot of different possibility. You can have alternating of the way the layer are tilting. You can have something with this layer going down, then up, so alternating. You can have something which is only going down, and you can have something which is continuous for the layer, or you can have a fracture of this layer forming these columns, and the shift between the block can be half of the layer, or could be any other value. So basically, they are all belonging to the same class, and it's kind of hard to distinguish between all the possibilities. And so more recently, I mean, it has been also some study on this other phase formed by this molecule, which is this dark conglomerate. So it seems, so this one should be published by this Boulder group very soon, actually. So it seems that, I mean, by phase fracture TEM, people could understand that in fact this phase is kind of analogous to this sponge phase formed in lyotropic liquid crystal, but here it's a sponge phase formed in thermotropic liquid crystal, so I cannot tell you too much about it, but it will appear pretty soon. And so basically, I mean, you have nanometer scale saddle splay curvature inside this phase, and so this is the phase which is macroscopy isotropic, but which is chiral. So the other phase, which has been also very interesting to study, is B4 phase. So there was a lot of debate about what kind of phase is this phase. So it seems it's kind of TGB phase, but on contrary to the normal TGB phase, where you have some block where the smectic layer in each block are straight. Here, I mean, the block forming this phase are twisted. So the layers are twisted, and so what you have some kind of tube. So these layers are twisted and form kind of tube, and these tubes are packed together, forming this kind of phase. So it's kind of variant of a TGB phase, and it's also, so it's twisted ribbon filaments, and you have also a huge saddle splay contribution here in this case. So I will not talk about this phase. So you can have also, because these molecules, they are not chiral. I mean, there is nothing which forbids that you can have also some polar phase, smectic phase, which are polar but without tilt of the molecule. So you can have also smectic phase, which are polar, and it has been found also in molecules with flexible tail, which are fluorinated, for example. And recently, there is also some phase which has been formed by Panera, by the Bancor molecule, but which are formed by only one flexible tail, which forms some kind of dimers and forms some smectic polar phase. So you have polarity, all these molecules, they are packing in the same direction in one layer, and they are packing in opposite direction between layer to layer, forming something, some kind of smectica antiferroelectric phase, which can be switched to give a ferroelectric, to give some ferroelectric phase. So what we want to do, we want to explore the phase behavior of this kind of molecule using simulation. So the first step we are doing, we are extending this simple system. We are working mostly with hard spherocylinder, where the interaction are only steric interaction in the system, and this known, I mean, from this work from Onzeger and this simulation which has been done by in the 90s, and here is a work from Frankel, where you can have isotropic phase, you can have nematic phase, but you can have also, which is more surprising, a smectic phase in this system, while you have only steric interaction. So basically what's happening is that you have competition between different kinds of entropy in the system. So when you are at low density, you have isotropic system because you have a strong entropy of orientation of the molecule, and if you decrease density, I mean it comes to a point and this orientational entropy, the system becomes jammed, and so it's better to get nematic orientation because you gain some entropy of translation along the long axis of the molecule, and then if you decrease again if you increase again the density of the system, then the system will get again jammed, and so you can form some symmetric layer where you gain some entropy of translation within the layer of the symmetric. So basically this is this kind of mechanism which is at play here. So basically what we did as a first attempt, we replaced our band core molecule by a dimmer formed by two spherocylinders which are attached together, and so it's also a steric model which is governed by the ratio of the length of the spherocylinder to its diameter, this opening angle of the molecule, and the pressure of the density. It's controlled by the steric effect, and so it's reduced to the spherocylinder system in the case where the opening angle is 180 degrees, and we studied by Monte Carlo simulation this phase diagram as a function of the pressure and the opening angle for one given parameter, which is this ratio L over D equal 5. So here are an example of the phase. So here with really kind of closed molecule, really bent, where you have isotropic phase, you have a symmetric phase, so here it's liquid inside the layer, and it's polar because the molecule wants to act, and you have a crystal phase when you increase the pressure, and here is the same example for molecules which are much less open, where you have also a nematic phase because the opening angle being much bigger, the molecule can translate one with respect to the other, and you have also symmetric polar phase. And here here I presented these two symmetric phase. So you have symmetric polar phase. So here what is represented, but I don't think you will see very well because I have already difficulty myself, but here you have basically one polar direction, so these arrows which are represented here are this vector which is along the apex of the molecule here. So you have one direction here in this layer, one direction like that of this molecule, and so on. So you have a polar phase, and if you increase slightly the opening angle, you have something which is non-polar phase. And so here is the phase diagram. So here is the opening angle, here from 90 to 180 degrees, so very bent to straight, and here is the reduced pressure or the reduced density. So you see that we have mostly nematic phase which appear when the opening angle is not too big, right? Because the molecule can translate one with respect to the other. We have the symmetric phase, which is non-polar, and you have also, when the opening angle becomes quite important, you can have also a polar symmetric phase in the system. So it's what is written here. So we didn't find any biaxial nematic phase in the system, and the nematic phase is vanishing for when the opening angle becomes large, right, because the molecule cannot translate, and we don't have any chiral phase, right? I mean, I told you that, I mean, this chiral phase are due to these two breaking of symmetry. There is this polar breaking, right, which we see here, but you need also to have a tilt of the molecule. So we didn't get any of this. So the next, so we also studied what was the stability of this phase. So we are studying the difference in stability between molecules where from layer to layer all the molecules are pointing in the same direction, and the case where the molecules are pointing in opposite direction. So between the ferroelectric and the anti-ferroelectric case, and we computed the difference in energy between the two cases. And what you see is that the anti-ferroelectric case is more favorable than the ferroelectric case. So why is that? So we are thinking that what's happening is that when you have this anti-ferroelectric organization from one layer to the adjacent one, you have more entropy of translation of the molecule at the interface. It's what is represented here. While when you have the polar ordering of the molecule, I mean the molecule cannot translate one with respect to the other, and so the entropy is lower in this case. And this is in good agreement with this other simulation we did on straight spherocylinder. When we drive the system from symmetric A to symmetric C, we tilt the molecule, and you see that the tilting of the molecule in the same direction, the synclinic tilting, has a free energy which is lower than the anticlinic tilting of the molecule. And we did the same simulation, or Matt did the same simulation, constraining the center of mass of all the molecule in each layer, and then in this case the free energy difference, while the free energy is the same in the two cases, so which seems to indicate that there is this effect which is at play here. So now, I mean, we'd like to know, to try to see, well, can we find also this B2 phase? So this phase which is formed by molecules which are tilted from, which are tilted in addition to have this polar ordering, you have this tilt of the molecule. And so what can we do for this? So what we are thinking is that in this nematic, I mean, one of the important effects is that you have nanophase segregation between different groups in the molecule. For example, you have segregation between this rigid aromatic core and the flexible tail, or you can have also some other kind of segregation in the system. You can have a shape segregation between the band core molecule or between some special tail in the system. And so this nanophase segregation, we are thinking that it produces frustration because there is a different preferred area density for different sublayers. And so this one gives rise to molecular tilt, and also this polarization play and this saddle play layer curvature that I was talking before. So, well, what makes us thinking this also is that we did also simulation of conventional liquid crystal, so it's atomistic simulation, so you don't see it very well here, but so we did simulation of this compound, which is a little bit special because one of the layers is chiral, but I mean if you forget this tail, right, which is chiral, and you suppose that you have two non-chiral tails, you have a normal conventional symmetric, and so we were able to get some symmetric C phase. So here is the whole molecule and here is the core of the molecule. So I don't think you see it very well, but there is a tilt in this direction here. So you have an anti-ferroelectric, you have an anticlinic organization of the core of the molecule. So it tilts in this direction, so it's alternating from one layer to the other. And it gave rise some kind of zigzag ordering of the molecule, which is something you see in experiments because the tilt you compute by X-ray and the one you compute by and the tilt you can compute by optical microscopy are different, and this one is in agreement with this observation. And what was important for us is that we turned off all the electrostatic interaction in our model, and so the tilt didn't vary very much. So we are thinking that the electrostatic interaction are not very important to induce this tilt. I mean, they contribute for sure, but they are not the main actor here. And so what we are thinking is that in fact the flexible tail in the symmetric determines the area density occupied by the molecule, and then the transition is driven by a competition between this enthalpy of the core, which want to pack close to each other, and the orientational entropy of the core of the molecule. So basically the competition is between the orientational entropy and probably translational entropy also of the core, and the orientational and the enthalpy and attractive enthalpy of the core of the molecule, which is similar of what's happening in linear monolayer, the tail playing the role of the core and vice versa in this system. So to study this, what we did, we extended our model. So here we have a spherocylinder which is connected with small tails, formed also by spherocylinder. So it's and everything is interacting through a purely repressive potential, and it's interacting only by 2 points, which are the minimum distance between the two spherocylinders in the model. And what's nice is that it's a model which has a smooth contour. And so we did some simulation in NPT, doing ND simulation, and we were studying this phase diagram of this system for also a given size of the core, which is LC over D here equal 5, and we have a tail formed by small spherocylinder of length 1, and we have 5 segments for the two tails. And so what's nice is that we get nematic, but we get also smectic, which is what's liquid-like, right, inside the layer, and we got also smectic C, where we have a tilt, right, in the system, and we got also some more exotic phase, which are probably exotic, although it's difficult to tell in this small system, which are presented here. And here is a phase diagram where you have, here is increase in the flexibility of the tail going from the left, and here is the pressure where you have nematic, smectic A, smectic C, and also you have all the zoology of the phase that you commonly find in rod-like liquid crystal. So, I mean, the thermal behavior is not too good because you see then the smectic C is occurring here at temperature which is higher than the smectic A, which is not too good here, and we are thinking that is due to the fact that our model doesn't take into account attractive interaction. So basically, I mean, this is what I told you, right, about this competition between the enthalpy of the core and the orientational and translational entropy of the core. And so when you increase the flexibility of the cell, you have a stronger nanophase segregation between the different parts, and so you stabilize smectic, and probably you need to include more attractive interaction in the system. So we went further and we applied this to our dimmer model. So we have still the core made by 2 spherocylinders, and we added this flexible tail, and we studied this system. So what we found something like this B7-like phase, where you have a modulation of the layer. Here you don't see, but it's really the core of the molecule. So you have a modulation of the layer. Here it's hard to say if it's really continuous or if it's really broken in some pieces. And the ordering is more exotic than liquid-like in the system, but the tail are completely melted. And so if you compare with this reconstructed electron density map from the work from Rosheka, you see that there is a very strong resemblance between this reconstructed electronic density and what we could get from our simulation. So if you increase the flexibility of the tail, what you do, you decrease the block size. So the block size, the layer size is decreasing with respect to the previous one. What we got also, this phase, which is probably B1-like, which is a phase where you have really colons, and you have a shift, a fracture between colons from half the layer, and this one is really liquid-like. We got also some phase where the molecules are tilting with respect to the layer, and the tail are melted, so which looks more like, and it's really exotic-like inside the layer or crystalline-like, so it looks like maybe more like a B3 phase. Is not that clear at this point. We have also this phase where we have some kind of block, so it's a chiral phase. The molecules are tilted with respect to the layer, and they form this small block. and this phase, which is even more exotic, where you have this colon, right? You have to think that you have very long colon in this direction going out of the screen. You have a colon and you have this kind of butterfly organization in the system. And you have also when the rigidity of the tail increases, so the tail becomes more rigid and you have a symmetry phase where the molecules are not tilted. And here is the phase diagram we obtain. So we have increasing flexibility here and increasing pressure here. So we have symmetric, non-tilted, polar, non-tilted. So here symmetric CP, it seems not really inside this model. While it's working well with only one spherocylinder, it seems we don't have tilted phase here, or the tilt is very low. So here is probably really a symmetric AP. And so you have this B1 phase, and going down you have this B7 phase where you have B1 is more this fracture and this block, this colon block, and when you go down you have this more modulation of the layer. So we went a little bit further, and what we did, we computed the free energy difference during the same simulation, starting from symmetric AP phase, and for different opening angle, driving the system, forcing the molecule to tilt inside the layer. So with respect to the normal to the layer, so here is a non-tilted and here is a symmetric CP phase, and you see that the free energy, it costs more energy to tilt when the opening angle, when the molecule is really bent, than when it's less bent. So we did another experiment. So this one was done for one pressure in the middle of the symmetric AP phase for the hardcore dimmer. So this one is just hardcore interaction. There is no flexible tail here, but we force the system to tilt right here during this simulation. And so what we did, what's interesting, it's at one point, I mean, when you force the system, when you drive the system to tilt from symmetric AP to symmetric CP, so here for a tilt with respect to the normal to the layer, which is 25.8 degrees, you have a symmetric CP phase, so you have polar order and you have tilt. And then when you go a little bit further, when you push the system a little bit further, what the system does instead of tilting, because it seems it costs too much energy, what it creates some, you have blocks, so you have columns which are formed, and you have fracture of the layers. And so you have column, so you have something which is more like a big one phase in the system. So it looks like, I mean, why the molecule should tilt is because we have this flexible tail, but then, I mean, what makes the formation, but the core has an influence to the formation of this block in the system. So we are at this point, and we will continue further to try to see what's happening in the system. So here is the free energy. So basically what we do, we start from this, so what we did from this simulation, we try to compute the free energy difference when we try to break half of the layer. So we take this system here, we divide it in two blocks, and we try to drive half of the system to shift one half of the layer with respect to the other, in order to fracture these layers. So what's happening is that it didn't work that well. Basically what you have ondulation. So you have ondulation till 85 degrees, where 85 degrees is a phase difference between the ondulation of the two halves of the layer. And then suddenly when you arrive to 90 degrees, you have the formation of the block. And here is the free energy difference from the non-ondulated phase and the ondulated phase. So this one was made for 120 degree opening angle, and here I summarize what we got for the different angle. So what's happening is that here we left the molecule free to rotate inside the layer, and it seems there is artifact here, so I'm believing that this one here should be above, but we didn't control this in the experiment. And the last step we did, so we compared here the free energy for two opening angles. So in red is the free energy when the system is ondulating, right here in red. for an opening angle of 90 degrees and 120 degrees. And in blue is what we obtained in the first simulation when we try to tilt the core of the molecule with respect to the layer normal. So it seems that it costs much more energy to tilt than to modulate, right? I mean, but here again, right, there is no flexible tail, so it's hard to tell what's happening in the system. And so we did also simulation with single tail banana. And just to finish, basically what we got mostly non-tilted phase. So we got an exotic phase, which is presented here, which is really exotic within the layer. Well, it's exotic or crystal, but the tail are really melted in the system, so it's probably exotic. And then you have also symmetric apolar phase, which is in good agreement with the experiments, because so far, well, I think it's very rare to have, in this one-tail system, to have a tilt of the molecule. And so here is the phase diagram. So again, increasing flexibility and pressure. So you have a symmetric AP phase. And so when you increase the flexibility, and you have mostly isotropic, and increasing pressure, you have some more crystalline phase, while exotic or crystalline phase in the system. And so to really conclude, so well, I mean, this minimal model, what we call it, this flexibility amplifying model can account for several of the key observed features of this material. So we have this spontaneous chirality, so it was this B3 phase, but we don't have this B2 chirality. So, and we have this modulated phase. We can reproduce them quite well. So it's what I was telling, that it's mostly due to this mismatch between this packing of the flexible tail and the rigid core. And we have these two, it seems, distinct mechanisms to produce this undulated or this columnar structure. So you have this block fracture, and you have also this spontaneous splay in this system. And these two effects comes from this competition, again, between this rigid core and this flexible tail. And again, we see that this symmetric phase, this symmetric polar phase are more prevalent when you have only one tail. But it's true that this B2 phase, which are really the main phase, well, one of the first phase found in this bent core banana wasn't found yet in this system, and we think that it's because our model doesn't incorporate this attractive interaction. We have only mostly repulsive interaction, so mostly steric interaction in the system.
Thanks. Thank you very much. Questions and comments? Please.
I would like to ask how sensitive is formation of the symmetric phases on your mask. I can hear.
Yeah. So you mean about the box size, you mean?
Yes, I mean if you use as a normal isotropic and regional sample, possibly some phases may not be possible to form, so are you using some other tricks?
Well, I mean, here you allow a shape deformation, right, of the box, so I think you can accommodate most of what you like. I mean, it's a triclinic unit cell, and so you allow deformation, right? The box can fluctuate, the shape of the box can fluctuate. But what is true, nevertheless, is that the simulations they are made for a given size, right? I mean, we have 1,600 molecules in the system. What I show about this ondulation and everything, and this free energy difference might be very different if you go to a bigger system, right? I mean, so this one I cannot tell.
Okay. Next.
Which algorithm did you use for this, and how long did it change?
So this one, I mean, this model with the flexible tail. This one, the one which is only rigid, is Monte Carlo simulation. So it's two spherocylinders which are connected together. They are very rigid, and so it's conventional MC simulation. The only stuff which is time consuming is to compute the minimum distance between the two spherocylinders, right? I mean, it's only, they interact only through one point, right? I mean, for the flexible model, I mean, it's not rigid body dynamics which is done here. So the model, I think what is running here is really like an atomistic system. So it's really beads connected by a spring. And so one of the spherocylinders, when we do MD, it's really two beads connected by a spring. So what you do, I mean, but it's a spherocylinder, well, it represents the spherocylinder. So you compute the minimum distance between two of these objects. And so you just apply this soft repulsive potential, so it's a truncated energons potential between the minimum distance, like you will do for the purely rigid spherocylinder, and then you move the system. But it's not rigid dynamics. So it means that, I mean, the length of the spherocylinder is fluctuating a little bit. The opening angle of the banana is also fluctuating a little bit, but you have a strong elastic constant. What you can do also, you can constrain the bond length or the opening or the angle. But it's really classical MD. It's really classical MD. It's not rigid body dynamic when you mix a rigid part with a flexible part here. But you can do something else. Right?
Did it take a week to do this? 2 weeks? Did it take a week or 1 month?
Well, I mean, for the it takes several days to run on. It's a serial code, so it takes several days to run the one which is completely hardcore, which is MC. For MD, it's a little bit more efficient, right? But yeah, nevertheless, it takes several days on serial machines.
This is discussed. No, you have time.
Okay. Can you just briefly explain? If you have just rod, not flexible, can you have symmetric A, symmetric C? No. Then if you have tail attached to this rod, can you have symmetric C?
Yeah. That's what I
for
should.
the same reason, so it's not necessarily bent for.
No, and actually, I mean, the point is that it doesn't work when you have bent core molecule. So it works, it really tilts when you have a rigid rod with two flexible tails, it really forms tilted phase. Right, this one works, it's what I presented, and you have very strong tilt. So it's really very significant. But when you put this flexible tail to this bent core molecule, we didn't get any symmetric C-P phase. So it means symmetric C polar phase. It didn't work, right? I mean, so there is something due to this bent core which makes that, I mean, it's harder to tilt. And so what we are thinking is that, in fact, I mean, we don't have attractive interaction in our system. And so it seems that, well, I mean, it's just a hypothesis, but what it seems you need to go to, you have to go to too high pressure in order to maintain this phase. And so pushing this molecule together makes that it's harder to tilt. Right? It seems it's something like that. It seems because you don't have attractive interaction, you need to go to higher pressure in order to have a symmetric or exotic phase or whatever, or crystalline phase. And then doing this, I mean, you forbid the possibility to have kind of strong tilt of this bent core molecule. But yeah, for only spherocylinder it works. You have tilted phase. The only stuff I didn't tell you is that the model is working even too well, because even when you go to the limit of really very high rigidity, so when you are close from really only one spherocylinder, you find also crystalline phase, but which are tilted. So there is some kind of artifact here playing a role, probably because, I mean, we have this interaction only through one point on each spherocylinder, and this one is really a problem. So it's why we think that we need to incorporate this attractive interaction.
You also mentioned that you use Lennard-Jones potential. What is Lennard-Jones potential without attractive interaction?
Well, I mean, again, right, I mean, for this hardcore, right, I mean, it's really steric interaction, it's Monte Carlo. When I do AMD, right, I mean, you need to compute forces, right, so you want to have something which is continuous, so it's not too good to use this hardcore system like a step, so we just use the Lennard-Jones, right, Lennard-Jones as an attractive part and a repulsive one, but you can shift the Lennard-Jones and cut at the minimum distance, so you have something which is smooth, but repulsive. So basically what it does, it renormalizes mostly the diameter of the molecule.
We've got a lot of time. Thank you very much. Next speaker, Slobodan Žumer.